Hello, everyone. It's Craig again. You might notice that this is not a real stream replay of our day 20 puzzle solving session. That is because I forgot to actually record that stream while I was streaming to Twitch rather. But I also wound up cutting off that stream at some point after I got to a solution to part one, but it wasn't especially efficient, and it was taking too long to solve the puzzle for part one, and so I decided to take a step away, get some sleep, think on the problem some more, and come back to it. So I do have a solution now, and actually now that I've come back and worked through the whole thing, without the pressure of doing it all right away on the live stream, I actually like this day 20 puzzle quite a lot, and I think it's one of my favorites this year for the way that each part of the solution kind of builds on the last one and leads into the next one. So I'm just making this extra video right now for the YouTube channel, so that we can kind of walk through through my solution, even though you won't see me live coding it, and just kind of show you how it works. So for part one, what we're being asked to do, and I'll go back to the calendar so that we can see the description of the problem. But basically, we've got puzzle pieces. We've got these different tiles, and each one of them forms an image, and you can kind of think of these of each tile as being 10 by 10 pixels, and each pixel is just on or off. It's, a dot for off or a pound sign for on. Or you can think of those as, black and white, a pure monochrome image. So what we're being asked to do in the first place is that these puzzles can, like normal jigsaw puzzles, you can, rotate them, any which way. And you can also flip them. You can flip them over horizontally or vertically, and you still have a valid puzzle piece. So the first part of this, we're kind of asked to find an arrangement of all the tiles so that all of the edges line up with each other in one, big square grid, and then get the IDs of the tiles in the four corners and multiply them together. So what I found, I got to a point where I had a class that represented the edges going all the way around a tile, and we could, flip that horizontally and vertically. We could rotate that. And I was trying to find, different rotations of edges and just basically doing an exhaustive search through the space where we try and line it, where first I would try and find, okay, what are all the other pieces that could possibly go to the right or below a given piece, memoizing those, stacking all those together. It really got... it was getting quite complicated, and although I did come to a solution that worked for the first part of the puzzle, at least for the test input, it was still way too expensive to run, and it was taking too long and not finishing when I ran it on the actual test input. It went on the actual puzzle input, because the Advent of Code website, for the example, gave us just 9 tiles that we would arrange in a 3 by 3 grid. But the actual puzzle gave us 144 tiles in a 12 by 12 grid. So the solution I initially had just wasn't cutting it. So kind of the first insight, though, was that in part one, you don't actually have to solve the whole puzzle. We do need to do that in part two, and we will get to how to do that. But in part one, all that's really important are what are the corner pieces. And although it's theoretically possible that there could be, all sorts of different arrangements, that something in a corner piece, like if you had something in the upper left corner, its top edge is at the very edge of the puzzle and doesn't have to match up with anything. Similar for its left edge. but you could imagine theoretically having a puzzle arrangement where it could line up with other stuff. You could even imagine a puzzle designed in such a way that it's like a torus, that the top wraps around to the bottom and matches with the bottom, and the left wraps around and matches up with the right. But that is not how this puzzle is designed. I found out this puzzle is much more straightforward, regular old jigsaw puzzle. And so what I found was that if you look at the edges of the pieces and you try and look for a unique pattern along the edge, left to right or top to bottom, and a corner piece will have two of its edges be unique. They don't match with it's like, for example, in the top left, its top and left don't match with the edges of any other piece in the whole puzzle. And so basically all you have to do is just count up. You have to figure out, all of the different edges of a piece. So, I have this tile class. It parses all of the rows of the input for a tile, and it stores them as this array of uint16s, one for each row, and we have this get edge strips method. So what this method does is it returns us all of the possible edges that this, in no particular order, that this tile can have, including when it's flipped. So image 0 and image 9 are the top and bottom, just the bits reading left to right. This vertical stripe method gives us the same thing for the vertical edges, red top to bottom. It just goes through, through each row and assembles up that vertical stripe. So we have, our left, right, top, and bottom here. And then to get the flipped versions, horizontally flipped and vertically flipped, we just take those same four things and we reverse those strings, and those bit strings, and we get the flipped versions. So we get the 8 possible edge configurations, or the 8 possible edges, including the flipped versions, for a given tile. And then to find the corners, all we do is we keep this count of different unique edges. And so for every tile, we get all of those 8 possible edges for it. We add to those counts. And then to find the corners, all that we have to do is we go back through the tiles and we see, okay, for each of its edges, are any of them totally unique? Meaning that same bit pattern doesn't occur anywhere else doesn't occur for any other tile in the image. And remember, like we said, there are ways to construct a puzzle that doesn't necessarily mean that those edges of corners don't match anything, but fortunately this puzzle is made in a simple enough way that they do. Because for certain that if you can find at least 4 pieces that have two unique edges like that, then you have definitely got the 4 corners of your puzzle. They could only possibly be corners. And fortunately, that's what we have with this puzzle. So we go through all of those edges for the tile, and if there's only one occurrence of it in the whole puzzle, then it's unique to that tile. It doesn't match anything else. Now, you see here I have, if the number of unique edges equals 4, we consider it to be a corner. Why 4 and not 2? It's because of those flips, because of those reversals. We have 2 edges. Like say again, we're looking at the upper left corner. Its top and its left should be unique, but if you flipped it horizontally, then the top edge would be reversed. If you flipped it vertically, then the left edge would be reversed. Now, it would still be a valid corner piece. Might be a valid corner piece at a different part of the puzzle, at a different corner of the puzzle, but basically, even though there are only 2 in the proper configuration, it will actually have 4 distinct bit strings because of that flipping property. So we find all the tiles that have 4 unique edge strings, 4 unique edge bit sequences. We check that there are exactly 4, which in this puzzle there are, and then we return the IDs of those tiles. And so, and then once we have the IDs of those tiles, we just multiply them all together. We do it as int64 instead of just int because the product is quite big and it would overflow a regular 32-bit int. But we get the product, and that gave us our correct answer for part 1. So the key to part 1, I think, was realizing that you don't have to solve the whole puzzle. All that matters are the corners. Now in part 2, you do have to solve the whole puzzle. But having that insight for part 1 led me to be able to, led me to what allowed me to solve part 2. So if we look at the description for part 2 here, you're seeing that we want to check the image for sea monsters. So first of all, we have to, actually assemble the puzzle, get all of the tiles arranged properly, and then remove their borders. So we remove, 1 pixel around the edge of the whole thing, and then each tile becomes 8 by 8 pixels, and then we actually smush those all together, remove the gaps, and form our full image. So first part of part 2 is to actually solve the puzzle, get all the arrangements. Then, after we actually solve the puzzle, we just have to remove the edges from all the tiles, and smush them all together to get a final image. And then we will go on to look for sea monsters in the image. But before we talk about finding the sea monsters, we need to talk about, okay, how are we going to solve the actual puzzle? So you'll remember in part 1, I really was only concerned with the edges of a tile. And I didn't even write anything that would rotate a tile or flip it. But to put together that actual image and search for a sea monster in it, in part 2, we're going to have to actually do that. So I made this other class. I put it in a separate header, and I could actually go back and retrofit my part 1 solution to use this as well. But I made this bit square class, and this bit square just represents a two-dimensional. You can just think of it as a two-dimensional array of bits, and it can be 10 by 10 to represent a tile. If we just trimmed off the edge like we have to in part 2, it could also be 8 by 8 to represent the trim tile, and it could be much bigger and represent the whole assembled image, because that's also. It's a square of tiles which are also square, so the whole thing is square. So basically, you don't need a separate horizontal and vertical dimension. In this problem, they're always going to be the same. So the actual representation of this dim is the dimension. So if we had, for example, 10 by 10 for a tile, it would be 10. And then we have a vector of uint64 to represent the actual bits in this. So we just pack them all in here, and so this offset method tells us what position, because this vector is one-dimensional. This offset method tells us for a given y and x what is the actual bit position in this representation that the bit we're looking that particular bit in the grid we're looking for is. So we just multiply y by the dimension, add x. So we have each row laid out consecutively, and then each position within a row, each x position inside that. And then, because all of these are 64-bit elements, I have these two constants, this k high shift, this k low mask. What this says is okay, we have to find the particular uint64 element for a given offset, we have to right shift it by 6. Which basically just means divide by 6, which is the same as dividing by 64. So we find, the starting uint64 element. And this k low mask, this is 64 minus 1, so it's 1 bits in everything up to the bit that represents 64. And we can AND that with the offset and get the bit offset within the word. So I can kind of show you, like, it'll become more obvious how we use this stuff in the set and get methods. So like this get method, if we want to find out whether a particular bit at a given y and x coordinate is set, we compute that offset, and then we get one uint64 word from that vector of uint64s at the offset right shifted by k high shift, which is same as dividing by 64. Then we AND that whole 64-bit word together with a 1-bit left shifted by the lower part of that offset, and if that is non-zero, then that bit is set. And if it's 0, then that bit wasn't set. And so the set method is kind of just like the mirror image of this. You know, we go to that same position that in rep, we have that same individual bit to represent the lower order bits of the offset. And if we are setting that bit to true, we're setting that, or just to 1 to set it to on, we just OR that in, make sure that bit is set. If we're setting it to false, we do AND with the inverse of that individual bit set. So every other bit except that one will be set in the mask. We do an AND, so we leave everything else the same as it was originally, and we just clear that 1 bit. That's how get and set work for this. So pretty simple. It's just a packed bit array. You can think of it as. Now, the other things that this bit square method provides is you remember that in our solution for part 1, we needed a way to just represent the edges of a tile. You know, both horizontal at top and bottom and vertical at left and right. So we can represent those. I took advantage of the fact that the tiles are 10 by 10, and we never really have to deal with edges larger than that. So I decided, okay, let's just return those edges as uint16. And there's this check here to make sure that there is at least enough space, you know, within 16 bits to store them. But the way we build up the slice is very easy. We just go, you know, through we just go through one row, or these all together, and return the slice. There's definitely a more efficient way to do this, which is to mask out multiple bits. Like if the slice is just totally within words, you just mask out multiple bits and shift them. If it spans across 2 words, it gets a little more complicated. But I went for the absolute simplest possible way to do this, even if it's not the most efficient, which is just to go like 1 bit at a time, assembling it. And that turned out to be fine. And very similar, like it is almost, the method to do a vertical slice is almost exactly the same, except we just switch the dimensions. So instead of, you know, incrementing through different x dimensions, we hold x fixed and we increment through y dimensions. And this one you actually can't without, you know, like aligning the bits more carefully than we did pull any tricks to make that faster. But with these slice horizontal methods, we can get the first row and the bottom row for the top and bottom edges. We can get left and right for the vertical edges, because we have to match those edges up against each other while we're solving the puzzle. There's also this rotate clockwise method. This gives a new version of the bit square where we have rotated everything 90 degrees clockwise. So, you know, we create a new bit square with the same dimensions, and then, you know, we flip, you know, y becomes x, and x becomes the dimension minus y minus 1. You know, I actually didn't remember, you know, like the full matrix math for this, but I just drew myself a picture and figured out, you know, like where the coordinates map to each other to figure out these equations. Just took me a couple of minutes sketching it down. But you know, we get the values from our original, and then we set them to their new positions, rotated 90 degrees in the rotated version, return that. We can also flip horizontally and vertically. So, all that we do with that is to flip horizontally, we, Y stays the same, and X just gets reflected across to the other side. Flip vertical, very similar, just reverse the roles of X and Y. And then finally, there's this all orientations method. So what all orientations does is it figures out all the different bit squares you could get from a given bit square by rotating and flipping it. And there are at most 8 possible ones. And you might think, well, shouldn't there be 16 possible ones? Because you can rotate it from 0, 1, 2, or 3 times. And then for each of those, you can have your original or your horizontal flip or your vertical flip. Well, the thing is, for a perfect square, if you rotate it 180 degrees, that's equivalent to just flipping both horizontal and vertical. So you would actually get the same results from flipping both the original, both horizontal and vertical, as you would by rotating 180 degrees. So really, you just have to do the original, flip it horizontal, flip it vertical, flip it both. Rotate 90 degrees, flip it horizontal, flip it vertical, flip it both. And then you cover all the possible orientations of your bit square. And there's only 8, not 16. So you can see how we do this. We start with the original not rotated as base. We put that in there, flip horizontal, flip vertical, flip both. We rotate it clockwise once, do all the flips of that, and we've got our set of all orientations that we return. So all the different ways we can flip it. And finally, there's this count ones method, because at some point we have to count the number of pixels that are actually on in an image. All this does is goes through the whole representation, uses the built-in pop count. LL function just means long, 64 bits. It counts up all of the bits that are set in every word of the representation, and we get our overall total. So this class is kind of the key data structure that we're going to use in part 2, both to represent a configuration of an individual tile, but also to represent the big image that we stitch together at the end. So, we've got something that just easily allows us to access all of those bits, easily allows us to get those horizontal and vertical slices to represent the edges and match against each other as just integers, and something that will tell us all of its possible orientations that we can work with. So this bit square class is the fundamental building block that we're going to use in our part 2 solution. So if we jump over to the actual part 2 solution, you'll see first I've got this dump bit square function that just actually prints something out, because this was useful to me as I was working through step by step to make sure that all the images still looked like what they were supposed to, versus the examples given on the website. So we still have a tile class in part 2, and we still have this get edge strips, although now the tile class, it still has the ID to represent the parsed ID of the tile, and it has but instead of that array of uint16s, we just use the bit square for its representation. So, we parse the whole thing, we build up this 10 by 10 bit square, and to get the edge strips, the possible edges all around, and their flipped mirrored versions, we just ask for the beginning and end horizontal and vertical slices from that bit square, and do something similar with the flipped horizontal and vertical versions. And then we also have this all orientations method, which gives us the whole tile in all its possible rotated and flipped orientations. We need some methods to see if like 2 different orientations of a tile fit with each other horizontally or vertically. So this fits horizontal looks at the left and right, and we just make sure that the rightmost strip on the left side so that rightmost vertical edge matches with the leftmost vertical strip on the right side. And for fitting vertical, it's the same thing for the top and bottom. So these just tell us whether left and right or above and below have edges that fit with each other. So we're about to get into the point now where we're talking about how we actually solve the puzzle. And my initial attempt at solving this was just never going to be efficient enough, because I was, looking for all the things that could, starting with one tile, looking at a given position, looking for all the given things that could fit, given what other tiles we had already placed, up and to the left, all the other tiles that we had placed around it. But the possible, and that would have been correct, and I did confirm it was correct just for the toy 3x3 puzzle input on the website, but it just would have taken way too long because there was way too much of a search space for it to go through. But then the real key here is to use the algorithm that you knew when you were 5 or 6 years old solving jigsaw puzzles, and that is start with the edges. It's really easy to find the corners and the edges, and you put those together. There are way fewer of those pieces, but you can kind of make the frame, and then you can go into the inside and fill in more and more. But that made the search space much smaller and made this possible. And I kind of was already hinted in that direction from part 1, just because I was able to find those 4 corner pieces. So you can find those 4 corner pieces. We can also find edge pieces that have 1 unique edge, although when we're counting it, because of the flips again, there's going to be 2. We can find the edge pieces between the corners, and then everything else is inner pieces. But the key insight here is that you can categorize tiles into these 3 different groups: corners, edges, and inner. There's only going to be 4 corners. So if you say start trying to solve the puzzle by placing something in the upper left corner, you've only got 4 choices. And in fact, since you can rotate and flip all of the pieces anyway, like any one of the because you can rotate anyway, any one of the 4 that you choose first, if the puzzle has any solution, then the first one you choose is always fine, because you're just going to get different rotations of the same solution. So you can pick any corner first, and you're going to get a solution. But then, you start with that corner, and then so you move to the right of that corner, and the next thing, and that's going to have to be an edge. And keep going to the right, that's going to have to be an edge too. So you only have to look through the edges to get all the way to the end of that row. When you're at the end of that row, it has to be another corner, and you have only 3 left to choose. And so, you can choose those, but basically, you get a situation where you start with the corner, you go along the top edge, you get to another corner, then you go below it, you got another edge, and then you have to start filling with inner pieces, but your search space is much, much more constrained because you have already filled out that whole top edge first. So to actually put this algorithm in the code, the first step is this Categorize Tiles function, which basically splits up all of the tiles, finds the ones that are corners, finds the ones that are edges, and finds the ones that are on the inside. So again, just like we did for part 1, we count up all the different all the number of occurrences of all the different edge bit sequences between tiles. And then we make another pass through. We count up how many of those are unique to a given tile. If nothing is unique, every one of its edges matches some other tile, and it must be an inner tile because something fits all the way around it. If there are 2 unique, then what that really means is just that one edge is unique. It's just that, both of its flipped versions are unique. So that means that it's an edge, but it's not a corner. And finally, if there are 4 unique, means 2 edges plus both of their flipped versions are unique, and it's a corner tile. So we categorize everything, and then these checks here are just to verify the correctness of that categorization we just did. There should be 4 corners. The edges should be the 4 edges minus the 4 corners, and the inner tiles should be everything except the outer rim of the puzzle, the outer edges. Okay, so we've got our categorized tiles. The next part is to actually just do a depth first search like I was trying to do before, but do a depth first search that is aware of what position it is and whether it's a corner, an edge, or the inside, and what's already been placed. And this depth first search has a small enough search space that it runs very quickly instead of taking forever. So there's this recursive function called solveImpl, which is doing that depth first search for us. So we have our categorized tiles that we can choose from. We have a y and an x that for each call to this function, we're trying to pick the puzzle piece that goes at that y and x position. And that y and x position is in this vector of vectors of bit squares that's the solution. So once this thing is full, it will be a 12 by 12 grid of bit squares, and each of those bit squares will be properly flipped and oriented so that it matches with everything around it and will be a full solution. And we're just going from left to right and then top to bottom. So we're starting at a corner, filling out the edge, getting to the other corner, then going to the next row below that, until we get all the way to the bottom row. And then this set of assigned tile IDs is just to make sure that we never reuse a tile. And because of the uniqueness of edges, it might not actually be necessary to keep track of these assigned tile IDs, but just in case of something tricky, because we don't necessarily know that all the internal edges are unique. They could match in more than one way, and it's worth being maybe a little bit paranoid about that. I wanted to make sure that we never reuse a tile after it's been assigned. So this recursive depth first search, if we get all the way to the point where y would be 1 past the n, then everything in solution should be properly assigned. We've got a proper solution. We can just double check that assigned tile IDs that we've assigned to everything, that it's equal to the dimension of the whole thing squared, and we can return true. True means that we found a solution. False means that the search terminated without finding a solution and we need to backtrack. So the next part is that we look for the possible tiles that we're maybe going to pick to fill in at this y and x position. We're only going to look at either corners, edges, or inner, depending on what that xy position tells us. So we're on a vertical edge, either the left or the right edge of the whole grid, the whole solution, if x is 0 or x is, the whole dimension, which if for the real puzzle is 12 minus 1. We're on a horizontal edge, either the top or the bottom, if y is 0 or y is the dimension plus 1. And if both of those are true, then we're in one of the 4 corners. So if we're in one of the 4 corners, the only candidate tiles that we're going to consider are those that we already know are corner tiles. Otherwise, if we're on an edge but not a corner, we're only going to consider those edge tiles. Otherwise, if we're on neither an edge or a corner, we'll only consider the inner tiles. This next part here, we just calculate when we recurse down. Once we do an assignment for the coordinates that we're currently on, the square that we're currently on, this just computes, okay, what's the next one we're going to assign? So we try to go 1 to the right, but if we're already on the right edge, we go 1 down and restart at the beginning of that row. So here, for all of the possible candidate tiles, which remember are only the corners, edges, or inner, depending on where we are in the overall puzzle grid, we're going to try each one of those possible tiles. Now, if the tile is already in that assigned tile ID set, that means we already used that tile at some previous position, and we can't reuse it again. So that's why we just check here if it's in assigned tile IDs, and if it is, we continue on to the next iteration, because we can't reuse that, at least at this position in the search. We then look at all of the possible orientations for that tile. And remember, there are 8 possible ones, considering all the flips and rotations. So this fits up and left. All that this function does is it looks if we're not at the absolute left edge, then we need to make sure that the puzzle piece that's already placed to the left of us, its right side matches our left side, that we line up with the one to the left of us. And same thing, if we're not at the top edge, we have to line up with the puzzle piece on top of us. So that's what the fits up and left function tells us, given what's already filled in the grid, the X and Y position that we're trying to fill in, and the possible orientation that we're trying to fill. So if a given orientation of a tile doesn't fit with what's already there above and to the left of it, then, it doesn't fit. We can't use it. So we go on to the next iteration. If it does fit, then, this is possibly a part of the solution. So what we do is we put that particular bit square, that particular orientation in this X and Y. We put the tile's ID in the set of assigned tile IDs so that when we go deeper into this search, we don't try and reuse that same tile. And then we recursively call solve impl again with the next Y position, the next X position, and all of the solution that we've already come up with so far. So if we keep on, and if this returns true, that means that we ultimately got down to this termination condition here where the entire solution is filled in, and we know everything matches. So we just return true all the way up because we found our whole solution. If this returns false, this means that the search terminated somewhere and we couldn't find a full solution given the prefix of the solution that we already had assigned. So if we don't return true, if it didn't return true here, then all that we have to do is we will remove this tile ID from the assigned tile IDs because it's no longer assigned because we tried it, it failed, so we're going to roll that back. And then we just, continue this loop through. We try the other possible orientations of this tile. And, if we don't get to a solution with any of the possible orientations of a given tile, we try all the other candidate tiles that are not already assigned here. And then finally, if we tried, every candidate tile that wasn't already assigned, tried all of its orientations, and none of them ultimately gave us a solution, then we return false because that means that given what was already filled in, above and to the left of this tile, there was no solution that we could get to through here. So we have to tell something, higher up that was previously assigned that, hey, you need to try a different orientation or you need to try different tiles. So this is still a recursive depth first search. But the really key thing is that we have a much smaller solution space to draw from because we know what's corners, edges, and inner, and it runs plenty fast, it turns out. So the actual solve puzzle implementation here is just to, hey buddy, my dog sees somebody out the window, so he is being a little rambunctious right now. Come on, buddy, settle down. So the actual solve method here is just we take the square root of the number of tiles overall, and we've got our dimension side by side. We categorize all of the tiles into corners, edges, and inner tiles like we did before. We build up this empty solution vector. This empty, vector of bit squares that is, the whole solution for the whole grid, 12 by 12. And this initially empty set of assigned tile IDs. We run this solve impl method. We check that it returns true at the top level to indicate that it, got the whole solution, and we return the solution. So this is the depth first search, the smart depth first search that actually solves the puzzle, and it gives us. This outer vector is, vertical, and there are inner rows of the individual bit squares. So this gives us our solved 12 by 12 grid of perfectly aligned 10 by 10 bit square image tiles. So if we go back to the puzzle description, what we then have to do after finding the real solution with all of the tiles aligned with each other, we have to trim off their edges so that they just become 8 by 8 instead of 10 by 10, and then squish them all together to form the actual image. So this is relatively simple to do. We're just going to make one very big bit square that is everything all stitched together. So what this does is, this outer dim is, the outer dimension is the, 12 by 12 for all of the tiles laid out together. The inner dimension is the 10 by 10 of the individual tiles. And then the assembled dimension is going to be the outer dimension times the inner dimension minus 2, because we're taking off 1 pixel all around the edge, so left and right, top and bottom, from each of those inner squares. We create this bit square for the whole thing assembled together. We go through all the y's. We compute what the equivalent y position in both the outer vector of bit squares and the y position in the actual bit square image in the inside is going to be. We do the same thing for x, and we just set the bits from the elements of the solved puzzle. So this just does all the math to fill in all the bits of that big bit square from the bits from the individual squares in the grid of the solved puzzle. So that's what it takes to stitch together an actual image. The next thing that the puzzle asks us to do after stitching together that whole image is to look for sea monsters. So we're looking for a pattern like this. And the interesting thing here is that it says the spaces can be anything. They don't have to be zeros or ones. It's just that these particular spaces in this image of a sea monster, these hash marks all have to be 1 in the pattern. So you can really kind of think of this as being like this first blank square can be 0. You can think of this as 0, 0 in the pattern, and then we have, a set of coordinates that all have to be true or be 1, but basically have to have their bits set in the image, and then we know that that's a sea monster. So what I did was I translated this little image here of the sea monster into a set of x and y offsets from that 0, 0, that top left corner. So I've got this little struct to represent offsets, y offset and x offset. And this constant array of offsets is just the translated version of the sea monster image. So the whole sea monster image is 3 pixels tall, 20 pixels wide, but it's actually only these 15 pixels of those 60 pixels that we're looking for and that actually have to be set. So we need to search for sea monsters in an image. So this contains sea monster at method, what it does is, given a starting x and y for the upper left corner of that sea monster image, if we look for all of these offsets, all of these 15 pixels that have to be set, and if one of them is not set, no sea monster. But if all of them are set, then we return true. We did find a sea monster at that given position. And then this contains sea monster just repeats that search over the whole image. So we start for all of the possible y starting positions, all of the possible x starting positions. Now you see we only go up to the one minus the y dimension because you can't, you can't look for something, look for a sea monster pattern on the bottom row of the image if part of the pixels have to go, like 1 or 2 rows below where you already are. Same deal for the right edge of the image. But we search through all the possible, top left corners for a sea monster pattern. Find any of them, we return true. Otherwise, we return false. So that's how we find a sea monster. We just look for all those 15 pixels at an offset from a given anchor to be set. So in the main function down here, we actually solve the puzzle. We assemble it into the big bit square. But what the puzzle tells us is that the that we may have to flip and rotate the image to orient it correctly in order to find sea monsters. So we actually need to try all of the possible orientations of that whole assembled image, and find one that actually contains an image of a sea monster. It turns out there's only one orientation that does. So the final thing that we need to do is to determine how rough the waters are in the sea monster's habitat by counting the number of set pixels that are not part of a sea monster. So what we need to do for that is we need to find all of the sea monsters. We need to remove them from the image, unset those bits that are part of a sea monster, and then count up all of the remaining set bits or on pixels in the image, and that will be our measure of how rough the seas are. So this remove sea monsters method, we basically remove sea monster if exists at and remove sea monsters. These methods are very similar to the contain sea monsters at and contain sea monster functions. It's just that, okay, so remove sea monster if exists at, we first just check if there is a sea monster at that position. If there's not, there's nothing to do. We stop right away. There is a sea monster at that position. We go to all of the pixels that are part of that image of a sea monster, and we set them to false. So we erase the sea monster from the image. We loop through all of the possible X's and Y's just like we did when we were searching for the sea monster. We remove all images of sea monsters from the image. And then all that we have to do is count the remaining number of set pixels, which if you'll remember from bit square, we wrote this method just to count all the ones. Count all of the set bits by just adding up the number of set bits for each individual word in the underlying representation. That's exactly what it does, and it spits out the answer for us here and gives us the correct count, or the habitat water roughness, and that gave us the solution to our puzzle. So, like I said, I wound up really liking this puzzle after I took some time away and thought about it a little bit more and came back, even though on the live stream, which unfortunately I didn't record last night, or maybe fortunately for you, since you're seeing, a nice completed solution that I can walk you through now, as opposed to me struggling with the problem originally. But I really like how each step kind of builds on the last step, how initially we're just thinking about edges and figuring out, what are the corner pieces, and then we can figure out corners, edges, and insides, and then we can figure out, okay, if we flip everything around, finding the actual solution of the puzzle. And once we find the solution of the puzzle, okay, let's think about how to put it together into one big image, and then look for patterns like sea monsters in that image. So each step follows on from the last one in kind of a fun way, and you just keep on building up, using the tools that you've already built. So I had a lot of fun with this one. I obviously did not make it, very well in the leaderboards on this one, having taken some time off and gotten some sleep before I really came back and did the solution. But I still really liked this puzzle today. As always, the source code is going to be up in my GitHub repository. That's at github.com/Craig-Chasseur/AOC2020. You can see that on the screen right now. You can also check the description down below for a link to the GitHub repository, and also links to where I do the nightly live streams on Twitch. I do plan on live streaming my attempts for some of the additional puzzles here. We only have 5 more days to go. And a lot of them are probably going to be a little challenging and tricky like this one, so I might not always get them right away, but I'm having a lot of fun with this, and I just want to say thank you to everyone for watching the live streams or for watching the stream replays on YouTube. I'm looking forward to solving the rest of these puzzles with you. Bye-bye.